explaining physics in heels. Today's lesson with Professor Diva, algebra-based physics, and today's lecture is units and vectors. In today's lesson, we're gonna look at the basic tools that we utilize when doing physics. Physics studies the universe, and in order to study the universe and objects and the way that they move, physics needs to make comparisons. And in physics, we call a comparison a measurement. For example, I have two different pairs of heels, a red one and a black one. I can compare their heel lengths by lining them up and seeing which one of them extends further from the ground up. In this case, the red heel is longer. However, in physics, we as scientists want to be objective. We want our comparisons to be the same no matter where we are and no matter who we're talking to. We have established that there are pairs of high heels in this world with different lengths for the heel. If I say, imagine a high heel, what are the odds that we're both gonna think of the exact same pair? Pretty low, right? You could think of my red pair or my black pair. So physics has come up with a way to be objective. What is the language of objectivity in this world? Numbers. Mathematics is the language of objectivity. If I say 2, we're all gonna think of the same thing. We're gonna think of the number 2. So how can we translate comparisons into numbers? That is where units come into play. A unit of a measurement is a standard object that we all think of when we make a comparison or a measurement. Here's a demonstration in heels. The unit of a turning combo in dancing is 1 full rotation. If I have 2 turn units, then I do 2 full rotations, or what we call in dancing a double turn. Can you guess how many units my next turn has? Did you guess 3 units? As a quick demonstration, if I want to measure, let's say this length right here, L, and I start with this unit, what I need to do is I need to count the number of times that my unit enters into my overall length. So let's see, we have 1 right about here, we have a second right about here, and we have a third. So we have 1 unit, 1 unit, 1 unit. So I can write that L is equal to 3 units. So what I did is I performed a measurement, meaning a comparison between an object that we study and a standardized object that we all can think of. Now, in physics, we have a lot of units that we're dealing with. But usually physicists work in an international system called the International System of Units. I wrote it SI because it comes from French and it says Système International. Now, the international unit for time, as you know very well, I'm sure, is the second. Why is it the second and not the hour? That's because some physics experiments are not that long. So it wouldn't help for us to work in 0.001 hours. Instead, we choose to work in seconds. For length, we have the meter. I am sorry if you're from America or if you're from a country that utilizes the imperial system, but I am both European and a physicist, so I will never in my life use feet. I always go for meters. Finally, for mass, we work in 1 kilogram. And you might ask, if we're working in seconds and meters, why are we working in kilograms and not in grams, right? Why do we add this K right here? And the truth is that objects are pretty massive. The objects that, for example, classical physics studies are on the order of kilograms. So it would be very laborious to work in grams. We would have to deal with thousands and thousands of grams, when instead we can just work with a couple of kilograms. Physics always makes things simple. If you feel like a physics problem is too complicated, you're probably doing something wrong. Always go for the simplest option. However, in physics, we have something even more powerful than units to help us keep track of our calculations. That is what in physics we call a dimension. A way for us to keep track of the ingredients that go into making of a new physical measure in terms of time, length, and mass. Let me explain. For a choreography, you need two things: different types of steps, and to keep track of how many steps of each type you need. For example, for this choreography, I need to take 2 steps to the right and 1 step forward. A physicist would say that the dimensions of this choreography are 2 right and 1 forward, because you take 2 steps to the right and only 1 forward. In physics, we have 3 main ingredients that come into play when we're building our experience of the universe. Those ingredients or dimensions are time, which we denote with a small t, length, which we denote by a capital L, and mass, which we denote by a capital M. Dimensions help us keep track of how certain properties interact with one another and how they transform in one another. We are going to study the action of speed, which is an average change in position in terms of time. Now, the symbol right here, the triangle, which we call delta, means change, or it means a difference between an initial value and a final value. In this case, a difference between initial position and final position. Same thing with time. This delta, again, means change. Let's think about it. What are the dimensions of speed? Our 3 fundamental dimensions are time, mass, and length. So, how can we channel those 3 dimensions into the dimensions of speed? Let's think about it. I'm going to write in brackets x to indicate that I am dealing with the dimensions of position. What is the dimension of position? Well, position is a length. Position is the distance from a point to the origin. So the dimension of position will be, of course, length. I think you can think about it too. What will be the dimension of time? Well, of course, it is time. So, in this case, the dimension of speed will be the dimensions of a change in position divided by the dimensions in a change in time. Change doesn't change the dimensions. So what is going to be the dimension of position? As I said before, it's going to be L. What's the dimension of time? It is t. So we just found out, and I'm going to rewrite it here, that the dimensions of speed will be length time to the minus 1. Nice! That's really cool. Here is an example of why dimensions are so incredibly useful. Let's guess Einstein's formula for how mass transforms into energy by looking at dimensions. First of all, I'm going to give you the dimensions of energy. They are mass raised to the power of 1, length raised to the 2nd power, and time raised to the negative 2nd power. So, what's the formula for energy in terms of mass? Let's think about it. The dimension of mass, as we established before, is m. The dimension of speed is going to be, as we proved previously, L t to the minus 1. We want to include m and c, c being the speed of light. Since c is a form of speed, the dimensions of c will be equal to the dimensions of speed. So they will, of course, be L t to the minus 1. Let's make a guess. Let's say that our formula for energy needs mass contributions and speed contributions. We don't know the contributions yet, but we can guess them. So I'm gonna say m is raised to the alpha power and c is raised to the beta power. Let's look at it. The dimensions of energy need to be equal to the dimensions of mass raised to the alpha power and the dimensions of the speed of light raised to the beta power. On the left side, I input what I wrote upstairs. m L squared t to the minus 2 needs to be equal to, the dimensions of mass are, of course, mass raised to the alpha power, and then speed has length to the beta power, time to the minus beta power. I think you already see it, right? We have m to the first power on the left side, and we have m to the alpha power on the right side. So alpha will be 1, and then we have length to the 2nd power, and here we have length to the beta power. So beta will be 2. So what did we just prove? We proved that energy is equal to m raised to the first power, c raised to the beta power, which would be c squared. So using nothing but dimensions, we proved Einstein's formula. Thank you so much for watching. Your support means the world to me. If you want more physics, be sure to subscribe and to hit that bell icon so you can be one of the first people notified when I upload a new lecture on a really fascinating topic. And if you want to get to know me better, check out my Instagram, Physicist in Heels, where I post reels daily. Well, see you next time.